Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you're watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on the YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
All right. Welcome, everybody.
We were just discussing how everything is a lie and I don't know anything.
Yeah, this is not uncommon that if you're studying electrochemistry, you're gonna run into situations like that.
This is the worst part about getting a PhD, higher education, all of it is that the more that you learn, the more you realize that you don't know anything. I don't think I'm like an impedance experiment, my own life, my brain, because I'm a sine wave where there are times where I'm like, I really feel like I'm like good at my job. And then the next week I'm like, I don't think I know literally anything.
Yeah.
I mean, about science, about electrochemistry, about anything otherwise. It really goes up and down like that. And it's like, it's moments like that. We're talking about circuitry and potentiostat diagrams and things. And I'm just like, I guess I don't know anything. Okay, cool. I'm back to that point. This is great. I feel like I learned a lot. I feel like I've been in my job for a while. I went to graduate school. I did a postdoc. Nope, all of it's for nothing. I don't know anything.
There's actually a really, I don't know, maybe I'll share this. There's a really nice visualization for that somebody showed me a while ago. And basically, it's, if you think about it, let's say this circle here represents all of your knowledge. And around it, you've seen
circle's too big, but okay.
Circle's too big.
If
you have all these question marks around it, right? And all these question marks go all the way around the circle, right? So it's just like total knowledge, right? Everything that's outside of this circle is stuff that you just don't know. But as you learn more things, your circle gets bigger. Sorry, that's very weird. You have more question marks.
There's more surface area. Yeah.
And you have a lot more questions as you kind of go around, you know.
So the bigger your circle is, the more questions you have. That's actually that's about
strangely beautiful in a way.
It is. It's also depressing because it's like, don't you just want to feel like you know a thing, and then as soon as you know a lot about that thing, you realize how many more things about that thing you don't know.
Yeah,
like electrochemistry.
But but here's the real question that I have about that, which is that in science, we're often presented with things where it's like, we don't know what the answer is, but nobody knows the answer.
That's true.
It's like it hasn't been discovered yet.
There is some comfort in that, where it's like, I don't know how this works. Well, nobody does.
Nobody really does.
Okay.
But then there's the like, I don't know how this works, but it is a thing that is knowable. And it's like everybody already knows this thing.
Well, would you say it's accurate to would it be accurate to say everything is knowable or no? Like, like in theory, right? I'm not saying it's practically. Right. Like in theory, it's anything could be knowable.
Yeah. So
I don't know if that's true or not.
So there are always degrees of So I would say I've thought about like learning stuff in levels and degrees. And Neil and I just had this conversation about like how potentiostats work. And we've always presented like the simplified potentiostat circuit diagram purely for educational purposes. Like it does the fundamental things to help people understand the nature of potentiostat operation. Now, we also know that there's thousands of components in an actual potentiostat, not just the components that we show in the circuit diagram. But we've also learned that there are other types of circuit diagrams themselves, and the diagram itself, which we know is already simplified, may not be telling, the complete story,
Right.
even from a fundamental perspective. I still believe that there's a lot of value in the simplified circuit diagram, where a lot of things are kind of unknown, because it still presents the issue, or the fundamentals about how something works.
See, I agree.
Hmm.
The problem that I have is like the last thing I said right before we stopped being muted, which was good that we were muted.
Yeah.
But it's like, when you have a diagram, you could have like 15 resistors
Hmm.
and capacitors and op amps and,
Yeah.
and other units, right? These are all circuit elements that are inside of a potentiostat, right? It's I mean, I always say it kind of in a silly way, but it's actually true to a certain degree. Like a potentiostat is just kind of a box of circuits. I mean,
Hmm.
so is a computer, so is anything electrical to a certain extent, right? But it's a box of resistors and some capacitors and other stuff. And it's like when we have a bunch of resistors in some pattern, or a bunch of resistors and capacitors, and we on a simplified circuit diagram, we just represent that with a box or a resistor, like an
Yeah.
aggregate resistor. There's actually truth to that, because they do insert, in some real mathematical way, like like you can, like Kirchhoff's laws, you can add up elements to be like a simply, but the reality is that it's actually like 14 different elements. What's the right term, on a printed circuit board, like
Yeah.
not glued, you know what I mean, like
Yeah, connected
connected,
together.
right,
We use an op amp.
right.
The op amp has a ton of components inside of it, but the op amp's just a triangle.
Right. That's my point, though, is like with the triangle of the op amp. I mean,
Yeah.
like, it's not really, it's kind of like a rectangle. But the point is, like, we draw it with
Oh, yeah.
two inputs and one output. So it's like, presumably, based on my very, very poor, as I'm discovering, understanding of everything, an op amp may not look like a physical triangle, but it is a device where it has two inputs and one output. We draw that schematically on the diagram that we've shown in our webinars, on our website, in various places. And it's like there's one input, and then there's another input, and then there's an output, and we draw lines going to different things. Well, physically, if that's true in any way, shape, or form, there is a piece of silicon on a printed circuit board where
Yeah.
there's two wires going in, coming from somewhere, and one wire going out. So, like, if what I drew on my PowerPoint slide or on my piece of paper is that wire goes to like this voltage, and in reality it does not, then I'm lying, or I don't understand it. Like, that's the part that's throwing me. It's like, and again, we'll talk about this probably at a later time,
Yeah.
you and me, or both of us, or one
Yeah,
of us,
one
right?
of us,
As with a webinar or with a new video.
Mhm.
But like, I gave a webinar. You can go to our webinars page. While we're there, why don't I shamelessly
sure.
show you our webinars page? And thank you again to anybody who came to my webinar a couple days ago. I did a webinar on some topic, which I should know right off the bat because I gave it, on impedance. It was this one, theory and fundamentals. It's like I think I was there.
Yeah.
It wasn't an AI avatar of me. I gave this webinar. So thank you everyone who joined. Much appreciated. You can watch it. The on-demand links are right here on our website. And next Wednesday, I'll be giving the next of this 5-part series. But my point is, in this webinar that I gave, here's Alex's voltametry one, and here's some other one. This one here, how a potentiostat works. I talk about the op amp. I talk about how it works and how the inlet and outlet is a feedback loop and all of these things. And then it's like, well, actually, it might be that one of the inputs actually goes to virtual ground or something. And so now I'm just sitting here being like, okay, well, if that's true, then what I just said isn't true. Like, what everything I talked about is like not true, or like one part of it's not true. And the optimistic answer that you would probably say is, well, it's a simplified diagram, whatever. And my response is, I lied, or I was led wrong. That wire goes somewhere else. It doesn't go to what I thought it went to, right?
Yeah, I know, and we will get to the question.
Yeah, we'll
the
get to your
questions that are
question, Shanta, in a second.
coming up, but okay. So I understand, like, definitely there's that point, but so it's often the case in science. I mean, I remember in chemistry, like when you learn about like Lewis structures and stuff like that, we use these like little sticks to show the bond between like two atoms or something. Is there actually a stick or two electron little dots that form like a line between our spheres in our head of what the atoms are. And it's
Yes.
like
There's a stick.
there's a st-
There's
there's
a
a stick.
microscopic quantum stick.
Yeah, there's a little
Yes.
quantum stick that like breaks the bond. It's like, well, when you think about bonding and all, it's like, oh, it's dramatically more complicated. And organic chemists, they're like the biggest offenders. Like, well, the electrons are just moving here and then moving there and shuffling around, and it's like, yeah, that probably happens, but there's a lot of like they don't describe the quantum mechanics that's happening for that. Like, we can barely do the quantum mechanics of like, well, actually, we can do the quantum mechanics of a lot of stuff, but it's so complicated if you get too deep into it. But no one's gonna learn anything if we if we're like, all right, we're gonna start with the hardest thing that we know and then work our way to simplification.
Well, the moral of the story is that I'm not going to learn anything the more that I continue learning. Because the more that I learn, the more that I think that I've learned nothing, and that electrochemistry is hard and circuit diagrams are hard, potentiostats are confusing, and I might just quit tomorrow. But until then, we
Until
have
then.
a live stream to run. So
Yes.
thank you for joining us
Yeah.
during this very interesting diversion. And let's get to it.
Yeah.
So Shanta has a question. Please show how we can do IR compensation in Aftermath software. We have Aftermath Blue, but I can't record a good CV. I even tried with Ferrocene, and I have used the default parameters to calculate RU. So I don't have a potentiostat live now, but what I can do is just look in the software with you and hopefully kind of walk you through it. So here's Aftermath Blue. So if you're having trouble getting a good CV, I have actually Ferrocene data here, but I'll just sort of open. Oops, I didn't mean to open an LSV. I mean, it's basically the same thing, but I'll open a CV just for good measure. Yeah. So basically, if you have a cyclic voltammogram or cyclic voltammetry experiment, I'm just put default parameters in here, right? The first thing that you have to know and to do when you're doing IR compensation is you have to set the current range. You see that there's like just random numbers in here because I have no potentiostat connected.
Those aren't showing up here, but that's okay.
It doesn't do it.
It won't show the different current ranges.
Then you know what I'm going to do? I'm going to share my screen.
Oh, okay.
I didn't realize that wasn't part. Like I know it's a tab or whatever.
Yeah.
Anyway,
I know.
This could be trippy for a half a second.
Yeah.
Okay, there we go. No, I think I saved it. Okay, so here's Aftermath Blue, right? And the first thing is you have to pick a current range. So like you'll have to know what current range is appropriate for your system and turn auto range off. It's not a big deal. Like if you don't do that and you try to run with IR compensation, it'll yell at you and it'll say, I can't. It'll say, please turn auto range off. But just so you're aware, and this is not specific to Pine or to Aftermath. Again, because I don't understand how potentiostats work. There's something about the circuitry that it must be on a set current range. This is fundamental. So it's on the advanced tab here. You can see there's working one IR compensation. So you can either set it to manual. If you know what the number of ohms are, you can put that in. Sometimes people put 80, 90% of that number. If you know that you had 10 ohms of, it's probably higher than that, but whatever. Let's say you had 50 ohms, you could just type in 40 here and do that. You can also do auto. If you ran, for example, if you have a wave driver and you did this method, impedance RU, when you did that, you might have got something that looked like it just said like it'll say, I don't know if the interface looks a little different. This data is actually from an older version of Aftermath. I don't have a potentiostat with me now, so I can't run it. I don't have like a Ferrocene in front of me, but it'll do something like this where it'll say what the value is. So it's 6 kilo ohms. And then what it does is it saves it. Again, I don't have a potentiostat, but you could look at the potentiostat settings, the device, and it will say like uncompensated resistance saved as 6.06 kilo ohms. Okay. So one of the options that you can do on this advanced tab is to set this to auto and then, whatever, 90% or something like that. And so if you ever retake the uncompensated resistance, it will always take 90% of that. So it'll adjust automatically. So that's how you do it, physically how you do it.
I'd say if they have any further questions,
let
us know.
It sounds like you're asking just how to do it. That's it. Like when you click perform now, again, I don't have an instrument here, but like when you click perform, it's with your current range, again, set an auto range off, and you set it here, it'll do it.
It'll do it.
The CV will be IR compensated.
Yep.
So whether your data looks good or not will depend on if you did this properly, if you picked the right value, if you picked manual and you didn't overcompensate or whatever. Like there's some caveats to that. Of course, errors can happen, but that's how you do it physically. Sushanta, I'll leave it there for now. I guess like comment if you need any more advice or just whatever. Other feedback, I suppose, about how to do it. But that's how you do it. It's on the advanced tab. Maybe you just weren't sure where to find it, I suppose. So feel free to comment again if you need more help, I guess. So
yeah. So first time here, welcome. Thank you. And next question is from Jenny Mentor. She says, what are some reasons that the ionic conductivity would be different in blocking versus symmetric cells? I'm off by an order of 10, getting 1 times 10 to the minus 4 Siemens per centimeter instead of 1 times 10 to the minus 3. And the literature, this is just from literature, and the literature is using blocking, and Jenny's using the symmetric cell.
Well, I guess the thing is, blocking and symmetrical are not mutually exclusive. Like symmetrical cells means there's the same electrode on both sides. The same electrode could be blocking or not blocking. So part of it is a I don't know what to call it, a semantic question here, but when people say blocking electrodes, so for instance, if you let me present two scenarios for you. So like in the context of a battery, if you had a symmetrical cell, for instance, you might use lithium metal on both sides, and you use a separator. And the reason you would do this would be to check or test the performance of the electrolyte and or the separator. So by doing this,
we ran into this issue though, actually, on Wednesday during live stream. We're back.
We're back.
Yeah,
I hope we're back.
Yeah. We're back. For some reason, it will just randomly turn off.
That's fun. It didn't do it during my webinar, I don't think, or did it?
It actually did.
Oh, cool.
And then I was like, what happened? So I don't know sometimes whether we're like clicking something.
I didn't touch anything. I don't think I did.
Yeah.
Anyway,
I don't think so. Anyway.
So apologies if we. I'll try to start over again here, but I'm not sure where I got.
No. You only got cut off just like right now. So
okay.
you're still describing
blocking
if you had
versus...
blocking versus symmetric and two lithium symmetric.
Right. Got it.
Lithium.
So again, so the point is, if you have a battery, for instance, and you put lithium metal on both sides, right, anode and cathode. I mean, splitting hairs here. It's both lithium, but you're doing that because it's like it's an infinite lithium source on both sides. So you're not really studying intercalation, deintercalation, capacity, anything like that. You have like infinite capacity on both sides. So all you're really studying are everything else: the mass transport, how well the separator holds up. If you're doing that, if you're studying like the electrolyte or an additive to the electrolyte, some people do additives for safety reasons, for other reasons. You might do something like that. Whereas like if you use, graphite and NMC or some other real electrodes, you could get convoluted results. And it's like, oh, well, my battery failed. It's like, well, did it fail because my additive was a poor choice or my separator was a poor choice, or was it because my anode and cathode was bad? It's like if you're trying to study the electrolyte or the separator, you don't want the other parts affecting your study, right? You want to isolate the thing you're studying. So all that is to say, lithium metal can be done as a symmetric cell, right? That's not blocking because lithium will intercalate lithium, whatever. On the other hand, you could have a different kind of symmetric cell where you have like aluminum or steel on both sides, like just some metal instead of lithium metal, right? You have like a some again, some steel or copper. Usually copper or aluminum are used as current collectors in real lithium-ion batteries. So you could have that on both sides. Now that is also symmetric, like it's the same electrode on both sides, but we call that a blocking condition because it won't intercalate lithium. In some of those cases, there's a small chance that you could plate and form dendrites and things like that. But basically, what we're kind of creating is a situation where, like lithium, by changing the potential between or the voltage across, those two sides, you're basically forcing lithium ions in this case, any ions, right? Just ionic transport, mass diffusion, mass transport, diffusion, whatever, in one direction or the other. But you might get like buildup of charge on one side or something of that nature. But it's blocking because it's like the lithium can't go in that case to the steel. It's kind of like a Warburg open, if you will, sort of situation. But that would be a symmetric cell that's blocking, right? Whereas with the case of the other case, it was also symmetrical. Lithium was on both sides, but when the lithium metal, when you apply a voltage across, essentially, lithium will not, it's not blocked. It will intercalate, as in reduce at one of the lithium metals. That lithium metal will technically grow, and the other side will oxidize, and it will lose some lithium to ions. So they're both symmetrical, but one is blocking because one is not really allowing any intercalation, deintercalation. Now, there may be reasons why you would do one or the other for experimental purposes to study modes of mass transport, or, as I said, effectiveness of electrolyte or separators. There's other things you can study, like tortuosity and stuff like that, like other properties. But the reason I bring all this up is for two reasons. One is to sort of clarify terminology of blocking and symmetrical, that these are not mutually exclusive terms. The other is that this could be part of the reason behind differences in ionic conductivity, because you might be studying different things. I guess I'm just trying to think, like the ionic conductivity, you might have different mass transport phenomena occurring if you have like two pieces of lithium metal, for instance. Again, apologies if you're not using a battery, but hopefully you kind of understand the analogy here. The mass transport is going to be a little different. The diffusion layers and some of the transport might be a little different when the ion, for instance, can intercalate at either side, versus on a blocking condition, it can't. The mass transport will proceed slightly differently in each of those cases. Like they're just not exactly the same physical situation, even though you might have the same electrolyte and the same separator in both of those cases, right? So lithium metal on both sides, right? So that's not.
Okay. So it's symmetric.
So
but
that's
not blocking.
That's symmetric, but not blocking, I would say, right? I don't know. I hope that makes sense. Like, again, you appear to have a symmetrical but not blocking situation, and I don't know. It seems to me you just have different. You have different. I mean, it's like the on the one hand, the transport might, in theory, be the same. Like ions are moving through, like diffusing in the same way, but when you solve like mass transport, like if you were to solve the system, mathematically, it includes boundary conditions. Basically, it's like you have like if you were to like Fick's law or whatever, it's like there's boundary conditions, and the boundary condition in each of the cases that I described are different. So I don't know if that means maybe the diffusion coefficient like should be the same, and so to your point, it would be weird to see different ionic conductivities, but just because you have different boundary conditions, that's my guess as to why you might see different situations occurring. I don't know. What do you think?
Yeah, I'm thinking a little bit about the system and what causes or what leads to changes in ionic conductivity. So Jenny Mentor 9191, you're telling us that you're using lithium on both sides. Can you tell us a little bit more about the system, the membrane that's being used, the electrolyte concentrations, things like that? When I think about ionic conductivity in batteries, I'm always thinking about because like I'm assuming like when you intercalate, uh, I'm assuming when some of the ions intercalate, you're going to get changes in the ionic conductivity. Would that be correct? It's like if you have lithium, and let's say, well, I wanted to say if you're not using lithium metal, but maybe when you're using lithium metal, yeah, you're using lithium metal, so the lithium ion is like plating on one side or the other side. Is it possible that when you're charging, discharging, or whatever the state of charge is, you have more lithium coming off,
I mean,
and,
maybe.
and hence,
Well, the other thing I think is that what are you talking about ionic conductivity? You're talking about the ionic conductivity of membrane, of the electrolyte, or the electrode? Which
or is it the ion? Yeah,
which things electronic conductivity are referring to? And then the other thing to
yeah.
think about, this part always confuses me, I'll be honest.
Hmm.
The unit is either Siemens, Siemens per centimeter, or Siemens per centimeter squared.
Yeah. Is it an area or is it a
I'll be
distance?
honest, I hate this. I hate this so much. It's like you'll have like um it's like you get the impedance or something like that.
Yeah.
It's like L over R times A is usually the equation. So it's like the
Oh
distance
yeah.
between the electrodes, so that's
L.
L over R times A over the resistance, which is in ohms, times surface area.
Hmm.
So you end up with 1 over ohms is Siemens,
Hmm.
and then it's length over length squared. So that's why you get Siemens per centimeter. But like sometimes if your impedance was done per area, then I guess you'd get like
Oh,
there's
yeah.
there's another length unit in there somewhere. This becomes quite problematic sometimes because like sometimes you'll see it like per surface area. So that's my first thing is just make sure you are comparing the units properly. Make sure it's not per centimeter squared. It's not a surface area thing because that you might just be
Mhm.
off by a length unit like that. Then that would explain an order of magnitude. If you have like 1 centimeter, you have to multiply by, then it
Yeah.
changes by or 10. It changes by 1 order of magnitude because you have 10 centimeters, something silly like that.
So
PEO and LITFSI.
yeah. So and then
Yeah.
I guess also to kind of like make sure that we're thinking about the question correctly. Jenny's comparing a literature value of 1 times 10 to the minus 3 to her value of 1 times 10 to the minus 4. So that is so if the ionic constant, there's a part of me that's wondering, okay, are there subtleties and differences in cell construction between what was done in the literature
That could be.
and what you're doing? Tiny differences.
Also, how are you measuring it? Are you doing impedance?
Yeah.
Are you doing short scans?
Mhm.
What's the measurement that you're using to get your conductivity? Because sometimes you use impedance, but then which resistance are you using?
Mhm.
Is it just the uncompensated the IR drop one, or do you have a semicircle and you're using a charge transfer resistance? Probably not
Mhm.
that.
Yeah.
It's probably the IR drop because that would more correlate with like
Oh, if
a short like you could scan. It's like LPR, so you're doing
oh,
PAS.
potential
Yeah,
stack. Yes. Okay.
that's like you might consider doing it's kind of like polarization resistance. So you basically scan at like 0.1 millivolts a second over 5 or 10 millivolts around OCP. Whatever the open circuit voltage is, scan very slowly and take the slope of the current versus voltage curve
Mhm.
because by Ohm's law, V is IR. So like whatever the slope of that is the resistance. That's another way to kind of obtain the resistance. You can't scan too fast, too far. It's kind of like impedance where you're doing a very small amplitude. But you could try to get the resistance or the impedance that way. Yeah, and then it could just be that there are some differences, slight construction differences in your cell compared to the cell you're reading about. Assuming you're comparing to a literature.
Yeah. It's hard to tell, and And it's like, oh, how do you explain like a 10, one order of magnitude, 10 times
Right.
difference in the ionic concentration to a degree? It's like I feel like we have to see it, because otherwise,
But I'll also tell you, cell construction is a huge deal. So like,
yeah.
if you're making a coin cell, if it's a pouch cell, whatever it is you're testing, cell construction can make a huge deal. I remember doing battery construction when I was in graduate school, and it was like, until I kind of learned how to do proper construction of a coin cell, like, it took practice. It's like I would get terrible results, and then I learned how to build it, and I get better results with the same materials. So
Mhm.
like that's actually quite disturbing, because then it's like, so you're telling me that there's a chance all of my data are poor just because I'm bad at making the stuff. Like that's
Mhm.
not, like you want it to be science, right? Like we would all fancy it to be, well, we're studying the performance of our material, and if our data is good, our material is performing well, and if our data is bad, our material is not performing well. But sometimes it's like our data is bad, and it's like our material's fine. We just didn't make the cell very well.
Mhm.
That's engineering. That's not science, right?
Mhm. Yeah.
And I think unfortunately, like, engineering gets in the way sometimes. So that could be part of it too. If you are, I don't know, new, or maybe you're not, and maybe you're pretty well experienced in the
Yeah.
laboratory in building stuff. In which case, that's great. If you're newer to it, it could be that you just need to practice construction of batteries um, and cells, and that could be part of it. Honestly, you know.
Yeah.
So
I'm also wondering, like, if you have a lithium salt and you have lithium electrodes, um, is it possible that well, I was just thinking, like, oh, is it possible that, like, some of the lithium by default, like, what if there is, well, I guess I don't know enough about, like, the charge always needs to be balanced in the electrolyte, but, yeah, I don't know, I was thinking about, like, could lithium ions just, like, be coming out, like, just dissolving naturally, in the electrolyte, but and that's changing that's changing the actual concentration of the ionic
well,
conductivity.
there are some issues. There are some potential trouble, just difficulties, because the membrane
Mhm.
is PEO. That's polyethylene oxide, I guess, and LiTFSI. So
Mhm.
um, and I think it's an ionic liquid. I think.
Oh, it's not ionic
I
liquid.
think
Okay,
TFSI is an ionic liquid.
I don't know. I have not.
I think it's. Um, I can't pronounce the name. It's like
Lithium.
TFSI is trifluoromethane sulfonyl imide.
Yeah.
I think it's an ionic. Is it ionic liquid? Or maybe it's just a salt. Maybe it's just a salt.
Yeah.
It's just a really complex salt. Usually people use LiPF6, but anyway,
Yeah.
um, non-aqueous solvents with lithium salts can be kind of wonky. It is possible. Um, I would assume that she's probably using,
Mhm.
a concentration in a solvent that's published and well, like, dissolves well enough.
Mhm.
Electrolyte can crash out in some cases. That can
Oh, yeah.
happen. That would affect the
Mm.
conductivity for sure. So if you're getting like crashing out of your um, salt on the membrane, that'll probably affect things for sure.
Yeah.
I don't know.
These
Um,
are just hypotheses,
yeah,
right?
a lot of these are hypotheses. Yeah,
Yeah.
without kind of seeing your data and knowing more specifics. Hopefully, some of these things give you something to think about. Maybe not, but there's only so much we can do with just the information you provided. But please give more details if you want, and if you have more specific questions, we can try to get into them. Again, to a certain extent, we're limited by just we don't have your data in front of us. We can't look
Yeah.
at it. So
Yeah. Or
um,
your cell.
that's true.
Yeah.
But some of that might be pertinent to your situation. So yeah,
Yeah.
hopefully. But if not, let us know if you have more questions.
Yeah.
Stupid man wants to know about things. So do you know what the Pine Research NI interface does? We're interested in the WaveNeuro FSCV potentiostat system. We don't know if we need the NI interface. NI stands for National Instruments. It's not a Pine product. So it's not ours. We resell it. So the WaveNeuro is a little fundamentally different than the rest of our potentiostat product line. The rest of our potentiostats connect to a PC with like a standard USB connection, and run off of our Aftermath Blue software, which I showed a little bit earlier. The WaveNeuro is a little bit unique in that it uses a National Instruments card to connect to a computer. So this is it's a little bit different, right? It requires an NI board. So National Instruments it's a company, right? It's a electronics company, or I don't know if whatever.
I don't know the
kinda,
details of their business. I just know they make these cards.
They make these cards. Yeah. They have other NI Macs, and they make data acquisition things. And I'm not the most well versed with National Instruments as a company, but you can certainly look them up. And they sell these boards. We resell them in a lot of cases as part of our. We used to, like a long time ago, with some of our older potentiostats, and we still do with the WaveNeuro. So that's what that board is for. It's a communication device for the WaveNeuro, and it is required. It's how the WaveNeuro communicates with the PC, and it's controlled by a software called HDCV that is controlled by the University of North Carolina at Chapel Hill. So if you're going to purchase a WaveNeuro system, there's just a little bit of a different situation. It's kind of a different, it's just a whole different academic world, basically. The neuro electrochemistry, FSCV, and that whole group of researchers. Trying to save money. Yeah, for sure. Well, we have a, it's probably, I don't know if it's applicable to the WaveNeuro. Our old potentiostat discontinued model called the CBP, connected to PCs using an NI board as well. And, you might be able to find an NI board somewhere else or on an older PC, possibly. You don't have to buy it from us. Like, again, we're just sort of reselling it for that case when people buy. But the community, the FSCV community, the neuro community is it's a slightly different variant of electrochemists, and the situation is just a little different. The software is a little different, and the types of experiments they're doing, like FSCV, are a little different. So some of those things are not exactly the same, but
yeah. To answer is kind of last question. There's a bundle that includes the National Instruments.
That's right. We have a bundle with it and without it. So
NI board. So
so if you don't have the NI board, you'll need the bundle with it.
Yeah.
So
I would almost say, before you even do most of that stuff, make sure you can get access to the HDCV software. Some people just have it, and once it's on your computer, you have it indefinitely. But if you don't have it, you should make sure you get it. And we know that the University of North Carolina, Chapel Hill, like electronics shop,
they
controls.
They sell the licenses, I think, or
licenses.
whatever, however they deal with it. That's the one part that's outside of our control. Yeah, exactly. The control software is maintained by UNC. So
so just make sure you do that before you spend a lot of money buying the bundle, then realize you can't actually get the software.
Yeah, I think on the webpage, I'll double check, but there's
that link may or may not work because it's kind of outside of our control.
Yeah, it is admittedly a tricky thing. It's, again, because this is a very, I'll just be honest, it's a very niche group of researchers, and a relatively small one at that. It's not one that we have software to support. It just isn't. I thought there was a link. I probably have to go to the right bundle. Let me go to
that's a good question. I'm looking for the link too.
I think there's a link in the bundle. I'm going to go to a web page and show you the bundle. View HDCV. So yeah, here I'll share.
Yeah.
So yeah, it looks like you probably found it, but I'll just show you for good measure here. This is the web page with for the WaveNeuro, like the one bundle, basic bundle. I think it includes the NI card, but whatever it is, you can see we have
I don't know if it's the basic bundle. I think the premium bundle has
the premium one. Okay, either way, it doesn't matter.
Yeah.
The point is just for the software. This is right here a link to I assume the UNC folks who can provide it. So so there you go. So that's the link, and you can try to do that. So yeah, I would definitely recommend kind of looking into that as well for it and everything.
Yeah.
We can definitely help. Our colleague Tim is usually the one who helps people
with
training and with operating HTCV primarily. So we can definitely provide some assistance. We just don't control the software directly. So I know it's sort of a bit roundabout. You have to go get the software from them. But if you do it, we will be happy to help you get up and running with it.
Yeah.
Sure.
That's right. Okay. That's good. So I think this was a comment based on the last conversation for ionic conditions. Just use blocking electrode. It doesn't matter anyway, since the high frequency excesses. Okay, so they're using the high frequency X intercept is the ionic conductivity.
Yeah. Basically, you're correlating the uncompensated resistance with the ionic conductivity.
Oh, okay. Yeah.
So it's the path between, which makes sense. Yeah. And that was why I was pointing out, it depends what resistance you're using to, you're doing impedance to calculate the ionic conductivity. So you're getting a resistance or an impedance value. That's why I was suggesting even just do a slow scan voltammogram possibly, so there's no ambiguity about which resistor you're picking. Because if there is a semicircle, you'd be getting like a charge transfer resistance, and that's probably not the right one. To your point, you could be getting the SEI resistance, and that's not the same as the ionic conductivity. So yeah.
Okay. Well, looks like those are the questions so far. We'll hang out for a while. Just to let people know, I think Neil mentioned this earlier, but there's some people who are still kind of joining us. But if you're unaware right now, Neil is doing a webinar series on electrochemical impedance. So if you're on our website, you can see it here in the upper right-hand corner. We always have this what's new, so you can always see new things that we have on our website. Workshops and upcoming webinars will always be on here. And so you can click here and you can register to sign up for these upcoming webinars. They're all basically free. And additionally, this is the next one that's coming up next week, Wednesday, is part 2. But on our YouTube channel, you'll be able to watch for now for free the first part. So if you're catching up, if you wanted to watch it and you got sick, you had some kind of an issue, or the 2 time slots didn't work out for you, you can still watch it on our YouTube channel right now. And it's easy enough to catch up on the webinar content. Even if you want to watch some of the future webinars, it's like, oh, I missed the first one. Well, it's here. You can watch it whenever you want on your own time. And then join us live on Wednesday, 8 a.m. and 4 p.m. Eastern Standard Time. And that converts into wherever you are.
It converts to your time.
To your time.
Yeah. Look, we have Google and AI now. So if you have trouble figuring out what 8 a.m. Eastern Time is wherever you live, it probably means you don't know how to use a computer at all. Because you can just Google 8 a.m. EST is where I am right now, and it will just tell you.
Yeah, it'll just tell you.
Hopefully time zones are pretty easy at this point in time to this day and age, I should say, to figure out.
Day and age.
Yeah.
And then other things that are upcoming, this summer we have workshops that are coming up. I'm still figuring out some of the details, but if you are interested, we're giving you some kind of information, just talking to you about electrochemistry, but we also go through experiences of doing the electrochemistry experiment, getting hands-on experience. So on the Pine Research website, you'll see upcoming workshops, and those will slowly start to get populated with new and upcoming workshops that you can attend and actually, meet some of us in person and get, some kind of hands-on experience with learning electrochemistry. So I just want to throw that out there.
Yeah, we do get some questions from time to time. I think we just got one recently where someone was like this week asking like, I want to learn electrochemistry, but I want like training in person. Like I want to work. They were asking about workshops like specifically. Yeah. So anyway, that is a thing I know for a lot of people who are sort of new to the lab, or maybe you're not even new to the lab, but you're new to electrochemistry. Workshops are a great way for you to like get that personal hands-on training. And they can be worth traveling to. So I know, you've done them in the past here in our backyard. We're in North Carolina. We may not have one this year, but we do them in Villanova and Rutgers, and there was one in Texas once. So, it's of course, if you're not in the US, it could be tricky to travel. But if you are in the US and you wanted some of that, it might just mean you have to, find a way to travel to, some
basically the Northeast.
Yeah, a lot in the Northeast. Yeah. But yeah, if you can find a way to get to one of these places, reach out to the people, running these workshops. In some cases it's us, in some cases it's the professor at these various universities. Those can be good hands-on training for you. So
yeah. All right. We did get a question that came in. I think we've
done this one before.
We've done this one before. Bro, can you teach me Daniell cell reaction?
Bro.
I
can certainly teach you the Daniell cell.
Well, yeah.
See if I can remember the potentials. I always feel like I forget them, but I could. Can you find me zinc and copper potentials?
Oh, the potentials. Yeah.
0.7.
I know it always adds up to like 1 point something, but
it's like 1.1 or whatever. I don't know. Find it for me if you can.
Daniell.
The Daniell cell. So it's a galvanic cell. Where the heck? What am I doing? Okay. It is effectively a separated galvanic cell, which means it's spontaneous. So you can imagine the typical way we do it is we have two vessels, two beakers. We have electrolyte in both of them, but different electrolyte. All right. I wonder if I have like a copper color. I just kind of have brown. This will be good enough. So this will be copper. Okay. And let me get zinc. Zinc is silvery in color. So
yes.
This will be zinc.
Yeah.
All right. I'm doing it like, fancy colored this time. So I can be super, super duper fancy. These are connected to some voltage source or whatever, voltage measurement. Okay. This right here is zinc. This right here is copper. And the electrolyte here will be something like copper sulfate, copper 2 sulfate. The electrolyte here will be something like zinc sulfate. Okay. The reaction.
Oh, you want the potentials or you want the reaction?
The zinc copper plates and zinc goes away, or is it the other way?
Yeah. Copper plates and zinc zinc dissolves.
All right. So copper 2 plus 2 electrons goes to copper solid. That's the reaction over here. I guess that would be where the reduction happens. So that would be the cathode.
Yes.
The copper is the cathode. I'll write that too. So sometimes you'll say cathode on this side.
Yeah.
All right. And then this right here is the anode because it oxidizes. Zinc goes away. So we have zinc solid metal goes to zinc. That's supposed to be a Z. 2 plus 2 electrons. So we have electrons that go wee in the external circuit. I'm acting like a child. I'm not sure why. Sometimes it's
They're actually saying we.
they
the
say
whole
we.
time.
Yeah, if you listen to them, you can't hear them because they're really small. They actually are saying we, like the piggy went we all the way home, right?
Yeah.
So the electrons travel through the external source. That's how you get your electricity. And to complete the circuit, we need to have negative or positive flow in the other direction, basically negative flow in the other direction. So we have as a salt bridge, sometimes it's like a cloth or a tube that connects the two cells, basically. And this is called a salt bridge, basically. I remember doing this in high school. I literally used a paper towel and it works.
Yeah.
And so you can imagine if negative charge is moving from right to left, we have to have negative moving from left to right, or positive moving from right to left. So we typically say we have SO4 2 minus ions. So negative are going to move in this direction. So that means there's charge balance. I have negative moving from right to left. I have negative moving from left to right. The net charge is 0. So on the right side, zinc is slowly getting eaten away and leaving and falling into the solution. And on the right side, let me get my little brown marker. Don't I have a brown? I guess I just have this one. It's growing. We're getting more copper. It's becoming enormous. Oh my gosh, look, copper. I don't know why I'm so goofy today. Sorry.
No, it's all good.
So copper is plating on copper. Right, it's plating into copper metal, and zinc 2+ is coming off. Okay, now the key is the potentials associated with these. So I'll just do this on a separate thing here. Tell me the potentials if you will.
All right, so
copper
for
2+,
copper 2+, for the plating, it's positive 0.34 volts.
0.34.
Yeah.
So E0 cathode is equal to 0.34, and for zinc it is negative 0.76.
Yes.
Yeah, I got it.
Yeah,
Great.
got it.
So zinc solid. Oh gosh, the drawing is deteriorating. Goes to zinc 2+ plus 2 electrons. Right. E0 anode is equal to minus 0.76. These are volts. I should put units because that's what scientists do. And so E cell, by definition, is E cathode, 0, minus E anode. So that equals 1.1 volts. And it's positive.
Yeah.
So this means it is galvanic. It means it's spontaneous. So electrolytic would be the opposite. If you got a negative voltage, that means it has a positive Gibbs free energy, which means that it is not spontaneous, because the voltage, the potential, here is positive. Delta G is minus NFE. That means we have a negative Gibbs free energy. Negative Gibbs free energy is by definition a spontaneous reaction. We call this galvanic. That's just the name. And so that's it. That's electrochemistry. So
that's the Daniell cell.
That's the Daniell cell.
Yeah.
Hope that is a good little bit goofy, but good explanation for you, sir.
Yeah. All right, we got a few questions coming from Doa. Doa asks, in electrochemical gas sensing experiment, how screen printed electrodes work without electrolyte? So and she has another follow-up question, a different question. So there still needs to be electrolyte. My observation has been that in electrochemical gas sensing, there is still some kind of electrolyte, even if it's like through a membrane or something, even if it's a very, very thin layer of electrolyte, the gas does necessarily have to get dissolved into the electrolyte, and then, and then the reaction takes place. So it's a very good question. And the truth is, you don't need a whole lot of electrolyte. Even in things like fuel cells, where you're adding hydrogen and oxygen gas, Well, that hydrogen and oxygen gas still has to go into the liquid phase so to undergo the oxidation and reduction reaction for the fuel cell to work. It doesn't look like there's any liquid, but there necessarily has to be because of the nature of electrochemistry and completing an electrochemical circuit. It's just the size of these. In fact, actually, what is it like? Like if you have too much liquid, it's actually bad
Mm.
for the fuel cell to work. Um, so yeah, in a way, there is a very small amount of liquid electrolyte that works in a electrochemical gas sensor on a screen printed electrode. Even if the layer is super thin, or even if it's like atmospheric water, like, oh, I didn't add water, but I'm not in like a clean room or a dry box or something like that. Like there's actually a thin layer of water on almost everything. And that can be enough to have some kind of electrical conductivity and make gas sensing work for the most part. So hopefully that answers your question. I don't know if you've had experience with any of those.
I haven't
kinds
done
of
a lot of
things.
gas sensing. I mean, like fuel cells are, you could
Yeah.
sort of say there's some gas sensing in that because it's gas phase.
Yeah.
But I mean, yeah, my answer was it doesn't.
Yeah.
You explained it more intelligently, but yeah, no,
Yeah.
there is electrolyte, even if you're not thinking that it's there.
Yeah.
Like there has to be. It's not physically possible to have the cell complete without ionic movement,
Yeah.
right? And that's what electrolyte is. It's ionic
Electrolyte
movement.
does.
Yeah.
Yeah. So hopefully that's helpful.
Mhm.
And then the next question is, please also explain pseudo reference electrodes working and what does that exactly mean? So there are often certain electrochemical cells and systems, in particular non-aqueous systems, where the potential or the quote reference potential is unknown. So in water, we have things like the standard hydrogen electrode under aqueous conditions, and we've kind of measured everything with respect to water or the SHE electrode. But whether you're in acetonitrile or DMSO or DMF, any number of a variety of different non-aqueous electrolytes, the potential of a reaction may be different. And so often what we do is we actually, instead of having a quote standard reference electrode, we will use a pseudo reference electrode in cases or instances where we can't use something that's more traditional, like say silver chloride or saturated calomel or something along those lines. So what ends up happening, there's usually a couple options. We sometimes also call this a QRE or quasi-reference electrode. And in the electrochemical cell, it's got you have some solution. You have your working. Let's say you have working. You have counter, and I'm just using these kind of symbolically. They can be anything, but the reference electrode can be a couple things. Usually, people will use just like a silver wire. So it doesn't have to coil, but let's make it just a wire. And this may be a AG wire, and we'll call it a QRE, quasi-reference electrode. Now, this electrode, and this is just what gets hooked up to your potentiostat. So your reference lead would go here, and the potential of this silver wire is all over the place. It's not stable. It's bound to drift. Tons of things like that. But what we end up doing is we add a molecule with a well-known redox couple that's soluble in your solvent. And so often you'll add something like ferrocene or ferrocinium, ferrocinium redox couple. So you'll add this in your system. And then what ends up happening is, let's say you're doing some experiments and you'll take some cyclic voltammograms and you'll get some cyclic voltammograms. I'm just gonna, maybe they look like this. So you get some kind of weird, some features, and then you have a nice kind of duck-shaped voltammogram, And then maybe you have some other feature or something like that. This here is your ferrocene-ferrocinium system. This is your ferrocene-ferrocinium system. And then this is what you're interested in. This is the response from the analyte. Well, maybe 1 hour later, you 1 hour later, you do the same thing, but you realize like, oh man, these peaks are over here. It's like it's at a whole different potential. And let's say this is the same axis. Right. Well, what you can do if it's like, well, this I found this at say minus 0.2, and this one was at minus 0.5. I'm just making up some numbers, but this also shifted. Your ferrocenium also shifted by the same amount. So whenever you're plotting, this is versus like the silver wire, whatever your potentiostat is spitting out. But when you actually go to plot it, and then when you're doing your data analysis or your data workup, what you'll do is you'll take this guy. Let's copy. No, that's not. That's the wrong tool. Where's my lasso tool? Here we go. We'll take this guy, and then what we'll do is separately, you'll be like, there we go. Take all this stuff away. You will simply say that here is 0. You'll shift everything over. You'll do your data analysis software, and you'll call this 0. So this, everything may get shifted in one direction or another, especially if if this was like 0.2 and it was here before. You'll just shift everything over with respect to the ferrocenium, the ferrocene-ferrocinium redox couple. Sorry. You'll just shift it over, and you'll report this potential. You'll report an E naught or an E or E1/2 versus the ferrocene-ferrocinium redox couple. And to be acceptable in the literature as a way of describing what is the potential of your system. So, or what's the potential of the redox or the analyte in question that you're trying to study. So the important thing to note with this also is that you should hope that whatever this doesn't work if your redox feature is also kind of on top of the ferrocenium. If it occupies the same space, it's very difficult, if not impossible, to use this convention. If that happens, what often we would do is we would find another redox couple that's very stable, and it just happens at a potential that's not, ferrocenium. So some people might use like a cobaltocene, instead, and it's just as stable. It works just as well, but it's at a different potential. And so the feature that shows up where there's overlap will now become clear because you wouldn't have ferrocene in your system. So I hope that makes sense. Let me know if you have any questions about pseudo reference electrodes and how to use them and what they mean.
So it looks like Mahmoud has a question. That's going to trigger me a little bit, which is okay. It's okay. It's been a while. Please explain how we can extract Tafel slope from CV. Do you want to get like behind a blast shield or something? If there's an explosion on this side of the table.
Well, I know that the answers you often can't.
I'll show you. I'll show you. I'm feeling charitable today. You're going to put up. So here's the deal. Okay. I'll show you how to do this. And you're going to have to put up with like 30 seconds of me on my soapbox. So the first thing I will say is that if you have CV data, you just took a cyclic voltammogram of any old system, you have hydrogen evolution or oxygen reduction or whatever you're doing some electrochemistry, and you just took a CV from like -1 to +1 at 100 millivolts a second. And you just say to yourself, I'm going to make a Tafel plot. you are probably doing something wrong. That is not appropriate. Tafel plots and the Tafel equation is a direct derivation of the Butler-Volmer equation. The Butler-Volmer equation describes electrode kinetics only. Okay, so this is like my spiel, my soapbox about Tafel. Okay, people very often just make Tafel plots from any CV or LSV data, and it means absolutely nothing. You can only make Tafel plots and Tafel data and extract Tafel slopes that have any practical meaning if you know that the current data is kinetic current only. There cannot be contributions from mass transport, diffusion, anything else. Kinetic only from like one reaction. That's it. So, all that being said, I'm going to assume that's exactly what you've done and have, and you're not making a horrible mistake. And we'll move on. Okay. So there's my soapbox about Tafel. Okay. So there you go. So in other words, this might be your CV. This is like Ferrocene here. So like Alex was talking about, right? What I'm not going to do is make a Tafel plot out of this because that would be a terrible example based on what I just said. If you have data that looks like this, you see how it goes up here. That's all like you might be able to get away possibly with like doing Tafel from like this part. So maybe that's what I'll do. Maybe I'll throw you a bone and I'll say, hey, look, all right, this part right here, I'll copy those data points. All right, I'll be charitable. Okay, that part right there, that's kind of the kinetic part right here. Right, this is the kinetic. If I went further, even here, I've probably already gone too far. But it makes a peak. That's mass transport's already taking into effect. It's not even appropriate. Okay, but let's say I have this data from a CV or an LSV and I want to make it Tafel. Okay. The way that I think about this, the way I always like to think about this is first think about what the Tafel slope is. This will inform you in terms of like the first thing to do with your data, right? The Tafel slope is like millivolts per decade. So right away, that should tell you the slope tells you what the axes of my Tafel plot should be. So most of the time with an LSV or CV data, you have current on the y-axis and you have voltage or potential on the x-axis, right? So if I have my slope of a Tafel plot is millivolts, like potential on the per decade. Well, first of all, the first thing I need to do is I need to swap the axes. Okay, so what I'm going to do is a basic math operation. I'm going to swap x and y. So I'm just going to flip these. So first of all, that's the first thing I'm going to do. Now, so I've got potential here on the y-axis. That's right, because now when I get a slope, I have millivolts on the y. It's y over x, right? So the second thing I need to do is the x-axis is millivolts per decade. Decade. What does decade mean? Well, decade is logarithm. It's a weird. It's not like 10 years. We're not talking about time. It's decade. It's 10x of current is what it is. So the second kind of transformation we have to make is we have to take we have a special thing in our software called Tafel log x. You're basically taking the logarithm, but you want to do see this is an absolute value. If your software that you're using or whatever you're using, be careful because of course, if you're taking the logarithm of a negative number, you can't take the logarithm of a negative number. So you have to take the absolute value. In this case, all of my current you see are positive values. Whoops. So it's not going to be a problem on the X data. But if I had reduction current or whatever and it was negative, you just should make sure you take the absolute value. Okay. So then now you see that the unit's gone away. It makes sense. I've taken the logarithm. Things basically are unitless when I have a logarithm. So this right here, I'll just rename it just for good measure. This is a Tafel plot, technically speaking. I have potential on the y-axis and it looks unitless, but it's decades of current. Okay. So now I've taken this CV or LSV data and now all I need is the slope. Now in our software, I just put a baseline tool here and just get the slope. So what you would do presumably is you'd get the most linear part of it. And in this case, you see it's 72. It's close to 60. It's pretty good. I mean, this isn't exactly accurate for the reasons that I described before. This is just a regular CV. I didn't intend on making this a Tafel plot, but ideally you would get something pretty close to 60 millivolts per decade for a 1 electron transfer, irreversible, heterogeneous electron transfer. Is that right? All that, say the right
Yeah,
words.
you said all the right words.
All the
Yeah,
right words, I think.
yeah.
Heterogeneous, for some reason.
Heterogeneous electron
Yeah, it's
transfer.
I always screw up homogeneous and heterogeneous when it comes to
Well,
electron transfer for some reason. But
well, it's
I can't wrap my head around it properly.
it's you can get the heterogeneous rate constant, but the
Right.
nature of the reaction is it's weird because in electrocatalysis, like homogeneous reactions and heterogeneous catalysis are all like two different, like they're basically doing like two different things.
Right,
So
right. It's whether the electron's
yeah.
tunneling through or not, but
Yeah.
most of the time it's heterogeneous
Yeah.
in this case. So, in any case, this is the Tafel plot, right? So basically, the first thing is to flop the axes, make sure potential's on the y-axis. Second is to take the logarithm of the x current axis. It does not matter, by the way, what unit your current was before you take the logarithm. It does not matter because you're getting decades. So if it started in amps or it started in microamps or milliamps, makes no difference. So just for what it's worth, just take the logarithm of it. Doesn't matter because the slope takes into account, like this x-axis here is -6, -5, -4. If it was -3, -2, -1, the slope would still be the same. So
Yeah.
it doesn't matter. So some people think about that. Oh, it should be. Don't worry about what the units of the current are. Once you take the logarithm of it, you take the slope, it makes a difference.
Yeah,
Okay.
I think the only like last thing that you'd do is you would move the potential axis so that it like 0 was the E naught of the reaction. It's the only other
Okay.
last thing, but
Yeah,
otherwise,
I'm not paying attention to the intercept at all. Is the point here?
oh yeah,
I'm
you're
just
not
looking
paying
at the
attention
slope.
to this. Yeah,
So you could in that way, right? You could correlate the intercept or whatever.
yeah,
So that's the
That's-
Tafel slope. That's a Tafel
yeah,
plot.
that's the Tafel slope.
So there you go.
There you
With
go.
all of the caveats that I gave, make sure that it is kinetic data only. That's how you make a Tafel plot.
Yes. Doe has a follow-up question. How can I prepare a miniaturized silver chloride electrode for biomedical sensing applications? You need to hire little elves to make little miniature electrodes.
No, what they do is they get the silver wire. They carry little silver chloride crystals one by one, and they smack them onto the
And
wire.
they smack them onto
That's
the
how
wire.
it's made.
Yeah, it's reverse mining. They don't
That's
mine
right.
the silver chloride off. They
It's
put
it's
the
placing.
silver. It's placing.
Placing. That's correct.
It's a placing job.
If you don't have tiny elves, the alternative is you can use electrochemistry.
Yeah. So generally speaking, for like biosensing applications and like using screen printed electrodes, there's no way to get a traditional silver chloride reference electrode on your screen printed electrode. What often people might do is they would add, they would have like a silver electrode and they would electrode deposit chloride on it. So you can oxidize the silver in the presence of chloride. Basically in the presence of chloride, and you would have silver. You probably have some silver oxide, but you'd have the silver chloride, and that would allow you to have silver chloride, but the potential of your silver chloride reference electrode would vary based on the amount of chloride that's in your system. It may be the case if you're doing this for like biomedical sensing applications, it may be the case that the chloride ion concentration in say blood is always the same. And so you could just calibrate your biosensor to like, the amount of chloride is always like I'm making up a 0.1 millimolar or something in blood. I made up that number. I have no idea if that's biologically if it's a biologically relevant
I got nothing.
yeah, if it's a biologically relevant concentration, but if it's always 0.1 millimolar, if it's always like that small, unless it changes by an order of magnitude, like 10 times, you would at best only observe a 59 millivolt difference in like potential shift. And sometimes what I've observed in biomedical sensing is that most of the time that's enough for you to sense what you're looking for. It's like, most CV peaks and things like that are always they're usually big enough, broad enough, and your sensor is optimized so that as long as you're applying +2 or plus 1.7 or plus 2.3, you're always going to get like a good signal, and it doesn't like convolute anything else. So even if that potential was shifting, you're always applying enough of the signal that you would always consistently get the same kind of result if you were sensing, say, I don't know, glucose or something like that. So that's my. I'm sure that there are ways that you could try to create something like silver chloride, maybe a very thin layer. You soak it in an electrolyte, and then you could seal it in like some kind of semi-permeable membrane so that it still has ionic conductivity. But I think that'd be very hard to do, and I don't know if anyone's done it. That's maybe a research topic in and of itself. So my hope is that that helps answer your question. I haven't done this
Let me answer it
myself.
another way that has nothing to do with screen printed electrodes. Because
Yeah.
if what you're talking about, I was just looking at some data that we
Mhm.
have from we have screen printed electrodes. We prepare
Yeah.
silver chloride traces on them and stuff. But one if another alternative is like you're trying to prepare a separate like silver wire with silver chloride on it, you're doing this, right? You're just doing this reaction. So this is like the silver chloride standard reaction. The potential is like positive 220 or whatever.
Oh, yeah.
So when it's in the oxidation, you just have to be above that potential to do this reaction,
Mhm.
right? So I was just looking at some data, for instance, about what we've done in the past, and I don't know if this is a perfect application for what you have, but like for instance, if you had a small silver wire, right, and you wanted to make a little silver chloride, so you want to basically you want to do this reaction and deposit some silver chloride on it. You want to do this reaction. So get a platinum counter electrode or something like that, maybe a reference electrode too if you want. But basically, you're going to connect it, and I'm just going to give you some numbers. I don't know if these are going to work perfectly in all situations, but get the surface area of your silver wire that's in solution that you want to put silver chloride on it. So get the surface area, and you're going to apply, roughly speaking, 10 milliamps per centimeter squared. Oops, geez, milliamp squared. 10 milliamps
Yeah.
per centimeter squared
Mhm.
for 60 seconds. So that's about what, like, just some back of the envelope stuff that like we've used for hours in the past. The exact amount of current that you apply in your potentiostat will depend on the surface area. But that's like just some actual numbers that you might be able to use. For instance, if you're trying to make your own wire, so get like, like 3 or 4 molar KCl or something like that as electrolyte. So there's plenty of chloride, right? And apply a positive current. So this would be like chronopotentiometry. Basically, this is a galvanostatic experiment, and apply this current for 60 seconds. So multiply 10 milliamps by whatever the square centimeter it is of surface area exposed. And you will, in theory, form a reasonable layer of AgCl on your wire. And then that will serve as a silver chloride reference electrode. Yeah, it can. So
Yeah.
That hopefully can help you if your preparation of a miniaturized electrode is outside of the context of a screen printed electrode, and you can do it with a wire. That might be a recipe that you can try.
Yeah, that's good. I have a similar kind of follow-up question, or similar set of questions about like screen print electrodes. Hi, please explain what parameters should be critically analyzed for lab-made screen printed electrodes before applying it to a biosensing assay. As scan rate analysis, number of scans are commonly performed for biosensing assay. If you are preparing your own lab-made screen printed electrode, there are a couple, I would say there's a couple basic things you should do. You should do a very simple cyclic voltammetry experiment. Can you actually get a CV of a regular, ferrocyanide, ferrocene type of system, single electron transfer, well behaved? Does that work? That is one parameter. It's not necessarily, do you do a number of scans or things like that. The screen print electrode, if it's made out of something like carbon, the quality of the carbon that you're using in the screen print electrode development is very important, because typically with a screen print electrode, you're going to be applying or maybe coating things onto that screen print electrode. So the preparation of the surface is typically very, very important. So that's really the main thing. I usually say, just do can you get good cyclic voltammetry, on it? And then I would do imaging to see what does the surface actually look like? Is it a very rough surface? Is it a very smooth surface? If you're going to be putting down some kind of biosensing assay on it, what's the configuration going to be? What's the area of the electrode? Those are kind of things, things like scan rate or number of scans that you do for some kind of biosensing. I think those things tend to come later. The fundamental platform, the template that you're using should be very robust, and ideally give good CV data for a well-characterized type of system. Low capacitance values, right? You don't want to have lots of double layer charging and capacitance. If you can suppress that, that would be very good. And their different ink formulations will allow you to kind of achieve or get that kind of result. So hopefully, Sidra, that's helpful for what you're going for.
I think this next one is, you're good at drawing this diagram better than I am.
Oh, what am I?
So Sushanta says, can you show and explain the circuit diagram of CV? I don't think that there's a misconception here that that's not the right. There's no CV is cyclic voltammetry, circuit but I don't know, if we're talking about the circuit diagram that exists between the electrodes in solution, that. Maybe, I don't know if that's sort of the question.
Maybe we need a little bit of clarification.
Do you mean the potentiostat circuit diagram, or do you mean where the resistances exist or whatever within within the solution? Between the electrodes that are in solution. That might be something to kind of clarify. You're talking about compensated resistance, uncompensated resistance, those kinds of things.
So if you can explain that, or give us a little bit more clarification what you mean by that, because the other interpretation is it's just a Randall cell.
Right. Yeah,
it's a Randall circuit. That describes what a basic CV is.
I mean, what I was imagining, at least as an answer for what you're talking about, is that you have, for example, working electrode, reference electrode, and counter electrode. Right. And these are all in solution. And it's you have, this is R comp. You have, I'm going to draw it in the wrong place, but it's this is uncompensated resistance here between reference and working. And then where I see, I didn't leave it. I'm bad at circuit diagrams. This is why I said you should draw it. I'm bad at circuit diagrams. Where does the working electrode circuit go?
Oh, it's right there
to the right.
Yeah.
So
that's fine. That
so
works.
Here, maybe there's
that's
a Randall circuit.
Yeah, it's a Randall circuit.
See, I drew the line poorly. I'm really bad at drawing circuits. You'd think of someone who teaches impedance all the time.
I thought this is. Yeah, I was what are you talking about? You're great at this.
I'm just bad at this. With this part, when it comes to just drawing a circuit that I'm going to fit impedance, I can do it fine. I don't know, but when I'm drawing the diagram with this, I don't know why I can't put it in the right spot. Anyway,
because I'm because literally all you do is you just you take exactly that and you just
put
You
it.
just put it there.
My
I'm
point was
you
like, do I
just,
put it to the
put
right or to the left? I guess I don't know. I guess it's to the right.
and to a degree, it
It doesn't really
kind of
matter.
doesn't matter because
Yeah.
the RU in a way is kind of like, I don't know.
It's
It's a
there
weird
between the
place.
reference. Yeah. Anyway, I don't know if that's exactly what you're referring to, but that's just like the circuit sort of the circuit diagram we show or draw for the electrochemical system. That's not and that's not specific to cyclic voltammetry. That's anything.
Yeah.
Like that's what's happening.
So yeah, give us more like clarification, and then we can
Yeah.
actually answer your question.
Yeah. The next question might be able to show with simulation. I guess.
Yeah, let's see. So, and also, sir, can you please explain a little about S-shaped voltammogram of EC mechanism? Why forward and backward currents merge together? Let me see if forward and backward currents merge together. So
I don't know what that means.
yeah, because so maybe we
is it
need
if
more
the
clarification on
If the
this one
C
too.
reaction is really, I'm trying to think, like I could make like a quick simulation. I don't know if you could too.
Yeah,
like,
but
I don't know
the
if what's referring to.
well, yeah, because here's the thing: S-shaped voltammograms. So I'm gonna draw this little thing very quickly, and then you can say whether it's
EC.
so in electrochemistry. When we talk about S-shaped voltammograms, it's like a voltammogram kind of looks like this, right? And maybe maybe there's a little bit of overlap and stuff like that. This kind of voltammogram is there may or may not be crossover, but this is what we call like S-shaped or S-shaped voltammogram, and it usually refers to not only the shape but it's a steady state response. Typically, steady state, and this is not necessarily it's not exclusive to EC reactions. Like it doesn't have to be an EC reaction to get this kind of response. So I need a little bit more clarification about if it's like, okay, why the forward, like, because when you say the forward and backward currents merged, it's like, well, they in this case they do. Like in my diagram, the S-shaped voltammogram. I think I'm sharing. Hopefully, I'm sharing.
Not now.
Not now. I think maybe I have a connection issue.
The connection hiccuped. I think. Hopefully, we're still all right.
Yeah. Let me stop sharing for a minute. Okay, let me. So in this case, yes, the forward and the back kind of merged. I put like a very little overlap, but this is just like you could get this with a rotating disc electrode. You can get this with a micro electrode as well. If you have EC, it can be like catalysis, like electrocatalysis occasionally has these interesting like S-shaped curves, but they all refer to a steady state. It means everything is kind of at equilibrium. And we can go over like what exactly does that mean. But I do want to clarify, just get clarification about that point. Because generally speaking, when we have this kind of overlap, it literally just means that the voltage and the current are completely like in sync with each other. So at a particular voltage, this current exists. At this voltage, this current exists. If I were to hold the potential here, I would always get this current value. It wouldn't change. It's at a steady state. In cyclic voltammetry, when you sweep the potential, it's not at a steady state. It would change immediately. Like when I hold the potential, it drops. But in an S-shaped voltammogram, that's maybe a microelectrode or a rotating disc, the current is at a steady state. If I just held the potential, it would be at this current value, indefinitely, as long as I held it. And that's why when you sweep, you get this kind of this S-shaped and there's kind of a merging between the forward and the reverse sweeps. So hopefully that answers your question, or if you want some more clarification, just because I'm like, I rarely see the EC mechanisms don't necessarily have to have that. But yeah, I digress.
It was a nice comment by Ahmed with other letters.
Says,
hi, I just want to thank you for all the live streams we've done. yesterday I did defense
Oh,
successfully. So yeah, we're
nice.
happy to hear it.
Congratulations.
Congratulations. I hope good luck to you in whatever future studies or not studies you're doing.
Yeah.
Happy to have been played a very, very small part of that. If we were able to help answer a few questions here and there, it's always nice to hear that. I always like hearing people people enjoy these sessions. We do them because we enjoy it, and it's it's nice to have this outlet, I think, for people to ask questions. We don't know the answer to everything, but we'll do our best to answer these questions for people. So
yeah.
And speaking of questions, there's another question. It's actually going to be the same drawing you just made, actually, in a lot of ways. In oxygen reduction reactions, what type of CV graph can we expect? Discuss the oxygen reduction reaction mechanism. Well, that's a loaded question. The mechanism can be a little bit. I think I've done this before too.
Yeah, we can go over the two different mechanisms, the peroxide and the water one.
Right, but the mechanism itself is a 4-step. I've done this before. I feel like I want to.
Oh, like the actual elementary steps.
Yeah,
you want to do that?
I wonder if I can remember it. I might have trouble remembering precise. They typically. Let me show you a few things. So, the oxygen reduction reaction. I'll talk about it for a little bit. If there are other questions, we can kind of kick me out here and talk about something else if this drones forever. But the oxygen reduction reaction. There's two main pathways. The good way is oxygen plus, I'll balance it in a second. I think it's 2 water, but oh, sorry, not water. Plus 4 electrons. I'm going to show the acidic version. There's an alkaline version. I'm just ignoring that for now. So bear with me. And that's 4, so 2 waters. 2 water. Right. And E0 is 1.23 volts. Right. All right. So that's the oxygen reduction reaction, the good one. I'll ignore the peroxide one because I assume mechanism they're talking about this. Like just this one. I'm just going to ignore it. The other possibility is that you form peroxide and it's a 2-electron pathway. I'm going to ignore that one for now. If you want to know about that one, I can talk about it. So typically people do this at a rotating disc and you actually get exactly what Alex just drew, which is that depending on how good your catalyst is, anywhere below about 1 volt, if this is 0 current or whatever, you get an S-shaped voltammogram. So you're looking for how you're getting a reduction current. So it usually looks something like this. And again, usually you're rotating an electrode. If not, sometimes it'll make a peak, I guess. But this is usually the type of oxygen reduction reaction data that you get. Now, here's the thing, if I can do this. It's usually a 4-step mechanism. I'm going to see if I can remember. It's possible I'm going to butcher this, but I want to try.
Okay.
I want to try. So I think it's like 1 electron at a time. You could think about it that way. So we have basically, oh boy. Okay. We end up with, I know. Hang on. I've done this before. I've done this on stream, but I used some help, and I want to see if I can remember it.
Why don't you just put oxygen? Something has to happen to oxygen.
Okay, oxygen.
Right?
Oxygen's here, right? Yeah.
Yeah.
Oxygen.
Oxygen's there.
It's like it gets absorbed. Oh man.
So there's a catalyst in here.
Yeah, there's a catalyst.
You want to say there's absorption to the catalyst?
4-step.
See, one of the reasons, like, we can talk about this, but
I need to look at it like for like half a second. And I swear I'll have it. I just like.
I'll also mention. Remember that this is going to be complicated.
Oh, for sure.
Like and people debate elements of the mechanism all the time.
That is absolutely true. So everything that I'm showing you is probably like 55 different people are going to have 56 different, ideas. I'm going to put ADS here. Oh my gosh, I can't write. I'm so sorry.
No, that was ADS.
But I just crashed PowerPoint by doing.
Oh, by hitting undo.
Oh my gosh.
Oh yeah.
All right. So we're gonna get there. I promise. I think I've just killed PowerPoint. Give me a moment, and I swear I'll get it back.
Okay.
this, I don't know why my undo is very stubborn and doesn't like to work. Hey, look, it recovered it though. That's
Oh,
good.
okay, that's good.
Okay, well, I still have the oxygen reduction reaction. All right,
All right.
I'm getting there. I'll show you the
Mhm.
mechanism. Okay. Here we go. So as I was saying, the mechanism, I lost the curve, but it doesn't really matter. So the mechanism is something like this. We have oxygen like adsorbed on the surface. Sometimes they put like a star to indicate that it's adsorbed. So I'll just put both.
Mhm.
Plus a proton plus an electron. And we get this sort of OOH. Again, they put a star or they put it's an adsorbed species. And I think it's got to have a minus, probably has a minus charge. And then we have OOH. Again, I think it has no, it doesn't have a minus. It shouldn't have a minus because they
end up being neutral.
They end up being neutral. Yeah, exactly. So this will be this sort of, I don't know, oxyhydroxide adsorbed species
Mhm.
plus another proton, the second electron step. You can see we end up with O. It's like sort of, it seems weird. It's like, oh, elemental oxygen plus a water. A water comes off. This is the first water, right? And you can just count, right? It's like two H's and an O. We're left with one O. And then we have our adsorbed oxygen here plus one more proton plus one more electron gives us OH adsorbed. And then that OH adsorbed, we get one more proton, the last one, plus the electron gives us the last water. And that these are like goes away, right? Like it's not adsorbed anymore. So it's something like that. So that's one conception. Now again, if you can read a bunch of papers and you'll get a lot of opinions about like the steps and the mechanism of it. This is like probably what I would say is the most common interpretation of the mechanism of the oxygen reduction reaction.
Mhm.
I think anyway. And as typical, the way this works and the reason why we tend to do a lot of the analysis we do is that no matter what the mechanisms are, someone usually identifies, I don't know which one it is, 1, 2, 3, or 4. One of these they say is faster than the rest of them, or sorry, slower than the rest of them. So we say one of them is rate limiting. And that's what allows us to use things like Tafel and whatever that sort of, assume one step, one electron transfer, or whatever.
Mhm.
Like you're not supposed to be able to do this because it's 4 electrons. It's like 4 steps or multiple steps or whatever. But when we say like, well, one of the step sub mechanisms is the rate limiting one, we sort of treat it like one step. That's kind of the justification, whether it's right or wrong, sort of definitionally wrong in some sense, but that's just what people do. So
Yeah.
anyway, I hope that's helpful for you. That's kind of my understanding of the mechanism. One explanation of the mechanism as I understand it. So.
Okay, we have a question from Mohana, and she asks, "Can you please suggest me some ideas about electrochemical analyses for PEM water electrolyzer application?" So make sure that the entire message didn't get cut off.
Sure.
Well, so electrochemical analyses, that just means electrochemical techniques that you can do on a PEM water electrolyzer. There's things like you can do the open circuit potential. That's one thing you can be looking at. You can do impedance spectroscopy of a PEM water analyzer. What are other things? I guess you're bringing up a polarization curve.
Yeah,
like
unfortunately, it's not
curve.
electrolyzer. It's the other way. It's a fuel cell.
Oh, you have a fuel
It's
cell.
a solar cell or a fuel cell. So, I don't have.
I guess
I don't,
LSV is the
yeah.
the
Okay.
technique.
So types of analyses for an electrolyzer. I don't have electrolyzer data like just on my computer. I have like fuel cell data, which is like the opposite. For an electrolyzer, the most common being water electrolyzer, but that's where it's the opposite of a fuel cell. So a fuel cell does the oxygen reduction reaction and the hydrogen evolution reaction, but they do it in a way that produces energy. So you rip apart oxygen
And hydrogen.
and hydrogen, and it makes water.
Mhm.
An electrolyzer does the opposite. It rips apart water and makes the other two.
Mhm.
So on an electrolyzer, you'll have water, the opposite of the oxygen reduction reaction. Two waters. So this is 2 waters gives you 4 protons plus 4 electrons. This is the same reaction I just did, plus 2 oxygen. Is that right? Wait, just one oxygen.
Just one oxygen.
One oxygen. Yeah, I can't count.
Well.
Yep.
Hold on. Yes. Yeah. That's
Yeah,
right.
that happens. That happens at the anode, and then on the other side you have. I'll just do 2. What I should do 4, so it balances. Yeah, whatever. Doesn't really matter. 4. We'll just do the same number. 4 protons plus 4 electrons. Since I have 4 above, it gives me 2 hydrogen gas. So this is like an electrolyzer, right? We're producing hydrogen and oxygen gas. This is at the anode. This is at the cathode. Okay, great. We have to apply a voltage to get this done. So if I have these reactions flipped, it's a fuel cell. In a fuel cell, we typically have voltage. So we start at about 1 volt, 1.23. That's the cell voltage. Okay. And this is our current. So with a fuel cell, I'll just put FC for fuel cell. We start here and we drop the voltage down. For an electrolyzer, I don't know, EL, whatever. We go the other way. So it's like that. It's something like that. So basically part of the analysis is to start at the open voltage, which is usually around 1.23, and raise the voltage that drives these reactions. I'm not going to show a lot of the math too explicitly, but basically what you're doing is you're pushing these reactions in the direction, in each of these directions, by pushing the voltage higher. That's what you're doing. And so you're producing oxygen and hydrogen, and you're studying how much current you get is required, how much power is required. So one of the analyses that you can do, for instance, is to do a slow scan of the voltage. So you can like scan the voltage from whatever the open is, 1.2 or whatever the number is, and scan positively. Usually you go pretty slowly. Sometimes what you can do is like, you can do that in piecemeal. So you can apply like every, let's just say 50 millivolts for 60 seconds each. So it's like you apply that potential for 60 seconds, you get a steady state current, you move it up, you apply the next one. So you'll get this, you can like produce this curve piece by piece, and then you'll connect the dots. That's how you can make this polarization curve. You want to make it pretty slowly, basically. So you take out IR drop as much as possible. That's one kind of analysis. Another one is a power curve. So what you do is you're going to plot at every point you have a current and a voltage. If you multiply those together, V times I, it's power in watts. So what you can also plot, for instance, is wattage or power. So this is power in watts versus, let me know if it's not hiding because of our face. I know.
Oh yeah, I'll just
versus current. And I don't know what it looks like for an electrolyzer. For a fuel cell, it usually looks something like this. You'll get some kind of maximum. It might look different for an electrolyzer. I don't have electrolyzer data to kind of play with, but basically, so a lot of times for a fuel cell, you're looking for like this point here, like what's the maximum power I can get, how many watts or milliwatts or whatever. That's one kind of analysis that you might do. So those are just a couple of ideas for electrochemical analyses that you can do. For water electrolyzer, you can do impedance. You can do an impedance experiment at different applied voltages or different loads to see how it looks. You want to try to you'll see multiple semicircles, probably one for the anode, one for the cathode. Study the charge transfer resistances and see if they're like pretty low. Hopefully they're pretty low. That means that your reactions are proceeding well. If you have a high impedance, high charge transfer resistance, it might mean there's something wrong with one of your, anode or cathode. Impedance it can be quite useful. Do it over time. You could like run the electrolyzer under a load, like produce hydrogen and oxygen for extended periods of time and see how long it lasts. If you apply slightly positive voltage or apply a current or whatever the control mechanism is for a while, and then measure the gas coming off of both sides. See, is it producing oxygen gas? You can run it through a mass spec or, GC, whatever you are to detect the gas. See how much gas it's producing, and then you can get like a Coulombic efficiency. You have X amount of current passing, right? You can use Faraday's law to assume the amount of coulombs that is. Use your stoichiometry and figure out how many moles of gas that should be producing, and then if you get that many moles of, less than that, then you have 80% Coulombic efficiency, 90% Coulombic efficiency, whatever. You could do experiments like that to try to see how well your electrolyzer is performing. Let us know if you need some feedback on anything I just said, if you need more specifics on some of that. But those are just some of the different kinds of analyses that, you would want to do on an electrolyzer to see how effective it is.
Mm-hmm.
So yeah, Mohana, follow up if you need any more feedback on that, but that's hopefully get you started.
Mm-hmm. We got a question. It says, for a reference electrode in a flooded cell, can I use silver wire instead of silver chloride? What is a flooded cell?
I mean, it sounds like you're talking about a fuel cell where the humidity is too high. It's like a gas phase kind of a thing where the water content is really high, but that might not be it.
Well, I'm doing just a quick Google search, and it's giving me a bunch of stuff talking about like lead acid batteries and
flooded cell.
Flooded cell. I might need to.
Yeah, I don't know if that's a specific kind of cell that I'm not familiar with, or it like flooding is a condition that is sometimes used. Like I said, it's used in fuel cells and electrolyzers. That term. Very often, because what you do in fuel cells and electrolyzers, if it's water especially, is you have like a Nafion membrane. Nafion requires water to conduct protons, and so we soak the membrane in usually sulfuric acid or something like that, and that gets it to work. And then when we flow our streams, our gas streams in our system, we use like oxygen and hydrogen on one side if it's a fuel cell. Otherwise it's water and maybe a carrier gas. But we humidify the streams. Like you send the gas through a bubbler, right, of water or whatever, and just then
3 electrode setups.
Yeah, so maybe this isn't exactly the thing. So
yeah,
it just sounds like a liquid phase system, right? I mean, that's
I
guess.
Yeah, I haven't heard the term flood cell, but you just clarified 3 electrode setup. So you can, but I don't know if there's a reason why. If you have a traditional 3 electrode setup, if you have a silver wire, so you'd only use a silver wire if if chloride was causing some contamination issues, and even if it was, you would want to use something like maybe a saturated calomel electrode instead. But silver wires just by themselves don't have a stable reference potential. So unless you add a known redox species, which I talked about earlier during this live stream, someone asked about QREs, pseudo reference electrodes. That's when you would use a silver wire, but you'd add a redox couple in to act as a kind of like a benchmark, like where is the potential relative to this known redox couple. So while you could do it, I think it's important to know that there needs to be, I would say there would need to be a scientific reason why you wouldn't use a silver chloride reference electrode if you're in an aqueous system, because I would, or if you're doing like impedance or something like that, and you actually get like high frequency artifacts, things like that, then it's like, oh, okay, yeah, sometimes you can use like a silver wire or a wire electrode if you're looking for a specific bit of data. But But yeah, generally speaking, I'd recommend silver chloride unless there is a scientific reason. Like chloride contaminates your system, you can't get it out. Use a silver wire. But if that were the case, you should go look at other types of electrodes that maybe like calomel is sulfate based.
No,
So
calamel's
chloride.
chloride.
Chloride. Sorry.
Mercury sulfate.
Mercury sulfate. Sorry, that's what I
Yeah.
was thinking about. Mercury sulfate. You can use a mercury sulfate reference
Or a
electrode.
double junction or a salt bridge or whatever it is.
Okay, he says I'm using it for electrochemical recovery of lithium. I need to use it inside my cell. So it's for lithium. It needs to use it inside your cell. Well, if your cell is a 3 electrode setup, then I still think that there's no, you can get a small silver chloride reference electrode.
I mean, I guess you might need to avoid chloride for some reason.
Yeah, maybe I have to
There
avoid
might be a
chloride.
reason why, yeah.
So, yeah, I don't know. I think that you, I need to know a little. I think we need to know a little bit more about what your system is, because the way you're describing your cell, yeah, I mean, in principle you can, but I think if you were publishing something, a reviewer might complain about it.
Mm-hmm.
So that's kind of my two cents. Like, why? If your electrolyte in the for recovering lithium is not is a non-aqueous electrolyte, then yes, I think that's definitely a better reason. It's like, oh, you have a non-aqueous electrolyte. If you're using something like if you use a silver wire, you can do that. You may even use, I guess, even a platinum wire can work. But yeah, if that were the case,
The thing is, electrochemical, I just don't like, obviously lithium ion batteries and things like that are non-aqueous.
Yeah.
But the electrochemical recovery of lithium I don't think it necessarily might need to be non-aqueous.
and it has to happen in the cell.
I don't know. No, yeah, I this is one of those like battery recycling kinds of applications that's really cool. I need to learn a little more about it, honestly. Because yeah, you can, you have this sort of spent material that has lithium in it,
Mhm.
and it's like, if you want to get the lithium out of it, you might use water, you might use non-aqueous, because it's an electrochemical process where you're going to either plate the lithium somewhere else to extract it, or you're going to get it in solution. Like there's probably ways.
Yeah.
So right to your point, it's like if it's a non-aqueous thing, you probably want to avoid the silver chloride because it's an aqueous, aqueous couple. But if it's an aqueous experiment, like you said, scientifically, unless chloride is something to be avoided, you probably can use the AgCl.
Yeah.
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 Hey, there's a question about the Nernst equation. Can you believe it?
Yeah, but we can answer it very kind of quickly. They're just asking.
It's minus RT.
Yeah.
Oh, sorry, I clicked at the same time you did.
Okay.
It's minus RT over NF, but it really has to do with conventions, which is to say we write reactions as
the log of products over
reactants, right? So
yeah.
So it's RT over NF times the log of the activity of stuff over activity of other stuff.
Mm-hmm.
We define that ratio as product over reactants. It would be plus RT over NF if you put reactants over products. That's it.
Or if you wrote, basically writing the reaction in reverse. So if instead of it being a reduction, it was an oxidation.
Yeah.
Well, then in that case, your sign's going to change. So that's why.
Right. Yeah. So we write reaction. So it's E is equal to E standard minus RT over NF times the natural log of the reaction quotient. For the standards of the reaction is written as a reduction, and we are talking about product over reactants of a reduction reaction.
Yeah.
Then it's minus.
Yes.
That's the correct set of signs, right? I hope that clears it up.
Yeah.
Let us know if you need more clarifications. I hope that's clear. Because you're right. It's like, oh, is it plus or minus? It could be either. It just depends on what your standards are. But that's what it is. Yeah. If it's a reduction reaction, products over reactants, it's minus.
Yeah.
So there you go.
Yeah. Yeah. So you didn't have to talk about the Nernst equation for that long.
I know.
Didn't have to talk about anything fun. It just need to get clarified.
Well, look, I got asked about Tafel stuff today. We needed a palate cleanser. We talked about the Nernst equation that makes everybody happy.
Yeah.
And it looks like we have maybe one more question we can kind of get to here. It says, in CV analysis, half reactions like OER or HER, the end of the CV curve gets folded while applying higher scan rates. Why I know why it comes folded. I'm guessing he's saying it's like overlapping.
Gets folded.
I'm thinking,
Yeah.
is this just a speed of the reaction coupled with a fast scan rate? Reaction speed's pretty fast for those though.
Yeah, I mean, it's possible. I've never fully understood, like, I mean, like what the scientific reason is why you get like this kind of like, oh, why would it go up and then it loop and then like,
Because you're going back in potential, but the reaction's still like speeding up, kind of, right? It's like the current is still going up as your voltage goes back.
yeah,
So it looks like it doubles back on itself.
yeah, kind of,
of.
yeah, it doubles back on itself. Yeah,
yeah, it is hard to wrap your head
Yeah.
around.
like the why.
Like
why do
why?
you get the kind of overlap in just even in CV? I've seen weird cases
Yeah,
where it goes up and then it
so
kind of
just to be
overlaps.
clear, I'm assuming when you say folding, it's that like for, let's say you're doing OER, right? So that's an oxidation reaction. So as you go positively, if this is your cutoff point, it's like it hits the end point, and in a good reaction, in a normal reaction, we would see it do this, whatever. But in your case, it goes here, and then it like keeps going up, and then it eventually sort of,
Yeah,
so it creates this intersection point.
yeah,
Now, in my experience, this intersection point is somewhat trivial. It's like if upon the vertex, where it turned around, right? It went this way and then this way. If upon that point in time here, went this way and then it went this way, the current didn't immediately go down. This is current and this is potential, right? If the current kept going up, it will necessarily have to fold, so to speak, right? If the current is going up and then I turn around and the current doesn't immediately drop, it stays too high. It will eventually have to cross itself and look like it's folded. Like, so some of this, it's just almost like happenstance, but like, it sounds like he's saying if it does that at really fast scan rates.
Yeah, it could be a double layer thing. It could just be like, yeah, the potentiostat reacting like fast enough.
I'm just
But
trying
it just means
these I guess that the problem is OER and HER have pretty fast kinetics, I think. So it's like
you could have irreversible absorption.
Yeah, maybe.
Or not irreversible absorption. It's slightly reversible, but like, oh, there's a
It's
little bit more
delayed.
current that got absorbed onto it or
Right.
something.
I'm trying to think. Yeah. I don't know if I have a good answer for it. It's really tough. It's a tough. Hysteresis is a weird phenomenon, especially with cyclic voltammetry. No, it's a good. I guess I'm trying to like think through why at fast scan rates you would see it, like, and not just as a general course of action. I know that sometimes kinetics can play a role in it. Yeah, I'd have to think about it and give a better formulated answer. I don't know that I can give a better answer right now. I'm trying to like it's like
sometimes actually I think at one point I was able to simulate it with there's a coupled chemical reaction that's also involved in this. And when you have a coupled chemical reaction and you look at the concentration of species as a function of like distance and time, you end up getting situations where, oh, there is this kind of odd concentration of species at the electrode surface at that particular point in time that it's like you're still getting a little bit more of the oxidation as you're moving backwards in potential. Like the reaction's still happening with high current.
I think the weird part to me, all of that is kind of what I'm thinking about too. Or like, yeah, if there's a coupled chemical, and it's like that wouldn't be that unusual because like oxygen will react chemically with stuff sometimes.
Yes.
So it's like if you're producing oxygen, for instance, I think what's weird is that I would expect that to happen at slower scan rates. Like you're going slowly, you're kind of producing oxygen for a longer period of time, and then right when you turn around, there's something happening and it kind of lingers or whatever. It's like here, it seems like they're saying like when you go faster, you're spending less time there, it's happening more. It feels like to me the opposite should be true. Just like if I'm guessing, If you were to
Yeah.
present that to me and say, what would that happen more likely at fast or slow scan rates? My hunch would tell me slow. So that's why I'm just hesitating. That's why I'm kind of like, yeah, I don't know why. I'm trying to think of an alternative explanation as to why it would occur more at fast scan rates than slow scan rates. I don't know that I have an answer for that. I think that's my point. Right?
Yeah, I mean,
I don't know. Like, what you're spending less time at
God,
the
I remember I
potentials.
simulated this at one point. I'll have to
Yeah.
try to do it again.
Well,
But
we might have to.
I was able to mess around with the rates of chemical reactions to
Yeah.
and changed it, especially with things like OER and was it OER and HER. With OER, like there's a lot of steps,
Yeah.
and
It might be that your
it's like
scan
there's
rate
lots
is
of reactions
your
occurring.
scan rate is on a speed that is commensurate with some chemical step of some kind, and it's
Yeah.
causing something of that nature to happen. Could be.
Yeah,
I guess. Yeah, I don't know.
yeah,
This is interesting.
I have to think about it.
Yeah.
CV
Yeah.
analysis.
So
We also don't know a higher scan. Like for us, a high scan rate's like a volt a second or something.
yeah, you might be talking about something faster.
Yeah,
I
you might
don't
be
know.
talking about something
Yeah.
faster. You may be talking about something slower, but it's still considered like high.
Yeah.
So, all
Just
right.
to follow up on this, you're talking about oxidized or reduced. The Nernst equation doesn't care. It doesn't care. It's the potential of the reaction is the potential of the reaction.
I think it's the reduction. So it's like A plus an electron goes to B,
Right.
and then when you write the whole thing out, it'll be B, the activity of B over the activity of A.
Yeah.
Let me bring it up. Let's bring it.
I think the point that I was making is like if you're talking about the reduced species or the oxidized species, either way, the E is the E.
Yeah.
The potential is what it is. It's the same potential. Like
You would you'd flip the sign. Like if I flipped this sign, the E would like instead if this was positive, it would be negative. And then I'd flip and then these would be different. And then but like it's like it's like if I make this positive, that's the same thing as flipping these two. But if I flip these two, it flips the sign. Right? Like if I switch the order, if I rewrote this as a positive with the activity of OX on top and the activity of red on the bottom, that would be let's see. Let me actually make sure that would be equivalent. That should mathematically be equivalent. So it's the two double negative or something like that. That's what you could do. You could rewrite it this way. But that's like for a reduction reaction, A or OX plus an electron going to red, it's the potential is equal to the standard reaction potential minus, and then it's the reduced species over the oxidized species. That is the definition. And if people write it as an oxidation reaction, then let's see. So if you
write it as an oxidation, E is equal to E0 plus RT over NF, ln of A ox over A red.
Yeah, and it would still have the minus sign, but this E naught, we report that as a minus if it's the ox. Well, hold on, maybe I have that right. No, that's not right.
The E does not change. That's the point.
Okay.
It's just the potential that you would have. You'd have a plus sign, and the ln would flip because it's the same.
Yes.
This is the thing.
That's right.
This is the thing.
Yeah, I got confused.
This is the thing that I think maybe you're confusing. The potential doesn't flip sign because you write it as an oxidation or a reduction. So, for instance, when I wrote the oxygen reduction reaction, let me share. I just did this for a couple of different questions that ran into each other, but I have these slides ready here. Right? I wrote this as the oxygen reduction reaction. Right? This right here, I wrote this as a reduction. Okay? This is the oxygen reduction reaction. This is the E0. This is not, forget about the ln part or whatever. This is the E0. It's 1.23. And then someone asked, did I even do it? I did it here. And then someone asked about an electrolyzer. And I wrote the oxygen reduction reaction. This is the same reaction, but I just wrote it as an oxidation because when you're doing an electrolyzer, it's opposite. Guess what? E0 for this is still 1.23. It is not minus 1.23. When you flip the reaction, the E0 does not flip. It's the same. The Nernst equation describes what the potential is with respect to this, but the E0 does not flip. So that's a critical thing here. The E0 of this reaction, whether it's written as an oxidation or a reduction, is always 1.23. It's not minus 1.23.
Yes.
That's not correct.
Yeah. Okay. And so that reminds me, there's another thing that, and this is one reason that sometimes we can all get confused.
Mm-hmm.
Whenever we're writing or balancing equations, we tend to, because it's like, if you have, like, when you were doing, I think it was the oxygen, I think it was the oxygen the oxygen reduction reaction, and you were going through some of the steps, and you cancel out you're canceling out electrons on both sides of the equation, right? You had the hydrogen side, you had the oxygen side, and you canceled out sides of it. Sometimes you can write the equation you can write the same equation as an oxidation or as a reduction. And I think what ends up happening is you end up flipping the signs. Like when you flip the reaction to get the electrons to cancel, you flip the sign, but you also flip which one's the anode and which one's the cathode.
Correct.
So there's a
the reason why the electrolyzer and the fuel cell calculations work.
Yeah.
Because in a fuel cell calculation, it's cathode minus anode.
Yeah.
Cathode is 1.23 positive. Anode is 0. So your reaction is plus 1.23. In the electrolyzer, 1.23 is now the anode. And the cathode is 0. So it's minus because you have to put energy into it to get it to work.
Yeah. Yeah.
It's the exact opposite.
It's the exact opposite.
But the standard potential is still a positive number. It's just that when you're calculating the voltage of something, it's one of them is being subtracted.
Yeah.
Because it's cathode minus anode. That's just how it works. Acid. But that number does not flip. E0 is thermodynamic and fundamental.
Yeah.
The Nernst equation describes how, like, the applied potential is related to the dissolved species. Right?
It relates. Yeah, it relates the it's the E naught is the
thermodynamic potential is at equilibrium related to the species in
the species in question.
Right.
Yeah, we just do a lot of stuff with anodes and cathodes and subtracting and adding. And that gets everything.
So anyway, the best case for you is to just stick to a convention. Don't get too tripped up over whether it's an oxidation or it's a reduction. Even if you have an oxidation reaction, try to write it as a reduction. Because then all of the sign conventions that we talked about before, that's where they are, right? And don't flip your E0; it stays.
Yeah.
So I see there's some other questions. Divina Stakursky. We're a bit on time here, so we're gonna kind of call it here. We tried moving this whole live stream back a half an hour, and apparently we should move it even further back.
Oh, we can't move it further back.
We can go 2 to 4. I don't care.
Go 2 to 5 if need be.
It's like we used to stop at 3 p.m. our time, and now we're at 3:30, 3:40. Seems to be there's always a deluge of questions at the end, no matter what. We could stop at 10 p.m. tonight for us, and there'll probably still be questions. That's just how it goes.
That's how it goes.
So we've gone a little over time. We do appreciate it. Apologies for a couple of questions. This is nickel oxide question and everything, but we're gonna kind of call it here, I think.
Yes.
We'll be back next week though. So if there are other questions, please join us next Friday around this time. And we'll try to get your questions. If you can show up on the earlier side, we'll get to them. Sorry we run, kind of out of time here. And join me next Wednesday. I'm doing my second of my impedance webinar. I'll be talking about Randall's and RC and different circuits and applications of impedance. You don't want to miss it. So join me next Wednesday.
Yep.
All
right.
Until then, thank you everybody for your questions and for another fun live stream. And we'll see you next week.
Mm-hmm.
Bye.
Bye.